This is fundamental problem 15 from chapter 16. In this problem, the center O of the wheel is moving with a speed of 6 meters per second. We want to determine the velocity of point A on the wheel. The gear rack B, that's here, is fixed. So they give us the velocity of point O. We want to find the velocity of point A. The first thing that we are going to do is find the instantaneous center of zero velocity. Now you should remember that whenever you have a wheel which is rotating on a fixed surface, the instantaneous center of zero velocity is the point on the wheel which is touching the surface. So that's here in our problem. We talked about something like this before when we said that for a rolling wheel, you should have static friction if it's not slipping on the surface as it rolls. So if you look at a point here, this point traces out this path, so it comes down as the wheel rolls. This is the wheel sometime later. This point hits the surface and then leaves the surface. It does not slide on the surface. So at this point here, at this instant here, the velocity of this point is equal to 0. So for a wheel which is rolling without slipping on a fixed surface, the instantaneous center of zero velocity is the point on the wheel which is touching the surface. Okay, so now that we have found the instantaneous center of zero velocity, our goal is to use that to find the velocity of point A. So we're going to use equation 16-16, and we're going to look for the velocity of point A. So we're going to change the B's to A's, and we're going to change the A's to IC's, and the velocity of the instantaneous center is 0, so we can get rid of that term. And we get the velocity of A is equal to the angular velocity crossed with the position of A with respect to the instantaneous center. I know where the instantaneous center is, so I can find this vector. Let's just do that now. The position of point A with respect to the instantaneous center. That vector goes from here to here. They gave me some distances on the diagram, which I did not put on my picture, but I can get them from up here. So the outer radius is 0.6 meters, so that's going from here to here. So this is 0.6 meters. So in the horizontal direction, we're going to the left, so that's negative 0.6 meters in the I hat direction. And then the inner radius is 0.3, so from here to here, that's 0.3 meters. That's going up, so that's positive 0.3 meters in the j hat direction, or we could say minus 0.6 I hat plus 0.3 j hat meters. So now, in order to find the velocity of A, the only thing I need is the angular velocity. Well, to find the angular velocity, I can use the velocity of point O, which they gave me. Let's just take the equation that we had here, and let's write this out again, but with point O instead of point A. So it's equation 16-16, with the A's being IC's and the B's being O's. So that would be the velocity of point O is equal to the angular velocity crossed with the position of O from the instantaneous center. That vector, 2.0 from the instantaneous center, is going up, and this distance here is 0.3, so that's 0.3 meters in the j hat direction. My angular velocity, well, I know the wheel is rotating this way, so it could, if I didn't know that, it would either be in the positive k hat direction or the negative k hat direction, but because it's rotating this way, that would be in the negative k hat direction. So I have VO, which is equal to 6 meters per second in the I hat direction, is, let's just call it omega k hat, and then if it's rotating in the negative k hat direction, this will turn out to be negative, crossed with 0.3 meters in the j hat direction. So when I do the cross product here, k hat crossed with j hat gives me negative I hat. So this is 6 meters per second in the I hat direction is equal to omega times 0.3 meters. K hat crossed with I hat gives me negative. K hat crossed with j hat gives me negative I hat. So omega is equal to 6 meters per second divided by negative 0.3. That gives me negative 20 radians per second. And we said this was in the k hat direction. So the angular velocity is in the negative k hat direction. So there are easier ways of figuring this out. So you don't have to treat it as a vector equation. You could just look at the magnitude and say the angular velocity is 6 divided by 0.3. So you don't have to show all the work that we did here, but I think it's helpful to see it. Okay, we're using this equation here now. To find VA, I have my position vector already, and now I have my angular velocity vector. So I have VA is equal to negative 20 radians per second in the k hat direction crossed with my vector for the position here. So that's negative 0.6 I hat plus 0.3 j hat meters. So I have k hat crossed with I hat. K hat crossed with I hat is j hat. So this is negative 20 times negative 0.6. And that gives me 12. This is meters, this is radians per second. So that's meters per second. It's positive because it's negative times negative. And k hat crossed with I hat gives me j hat. And then k hat crossed with j hat gives me negative I hat. So this is negative I hat. And then I have 20 times 0.3, which is 6, but this was negative and this was positive. So that makes this positive. 20 times 0.3 gives me 6, and this is meters per second. Let's write this as 6 I hat plus 12 j hat meters per second, and this is the velocity of A. So that concludes fundamental problem 15.